Hey there guys, today we're going to be talking about position time graphs, and we're also going to be talking about different multiple representations that we can use to model motion based on our constant velocity particle model. So this is the position time graph. Position is on the vertical axis, time is on the horizontal axis. In this case we're measuring in centimeters and seconds. Now if you think about the slope of these lines, the slope is going to be measured in the rise over run. Rise units would be centimeters, so it's going up a certain number of centimeters for every second. So the units for the slope is centimeters per second. If you think about the last video, meters per second is a measure of either speed or velocity. So if this is a position time graph, the first one, the red one, shows a slope of 22.5 centimeters per second. It turns out that that centimeters per second is the speed or the velocity for this car. It also tells me that the red one starts at a position of 75 centimeters. So this one didn't start at the origin, but we started 75 centimeters ahead of the origin. The black line shows that we have a slope of 45 centimeters per second, so this one's going twice as fast as the red line. But it started at an initial position of negative 150. Okay, and so we can see that both of these cars are moving. The red one's moving slower because it has a less steep slope. The black car is moving faster because its slope is steeper. And then right over here we can see that they intersect. So if this were to be carried out as like a lab and you set both of those cars up and they had those speeds, it would take 10 seconds for the black car to pass the red car. And so he passes them right at 10 seconds at a location of 300 centimeters. So this is just a little bit of what you're looking at when you're looking at your position time graphs. There's a couple things, and we're going to go into looking at it a different way over here. So we're going to be looking at how position time graphs work, and I have a different one that we're going to start with. So this one is a little bit more of a complex motion because we have three different lines showing technically three different motions. As we mentioned before, the starting position is labeled by the initial vertical intercept. So this one started at 20 meters and it's going up at first, so it's going forward. And we can see that we have three different slopes, so we're going to have three different velocities. The first part, it's moving forward because it's going up. And the second section, we have no slope. It's a slope of 0. So this is actually a section where the object is stopped. And then we have a negative slope. So therefore, that car is moving in reverse during this section of time. Okay, we can use the velocity formula, change in position over time, or displacement over time. We'll explain what the velocity is. So we started at 40, we ended at 40. That's our final position. We started at 20, so 40 minus 20, during that section of time, over those 4 seconds, it traveled 20 meters in 4 seconds. So we have an average velocity of 5 meters per second during that time. In the next section, it did not move anywhere. It was at the exact same position, so it traveled 0 meters over 4 seconds. So its velocity is 0. And the last section, it went back down to 0. It started at 40, so 0 minus 40 is negative 40 over the 4 seconds that it took to do this, and this one traveled at negative 10 meters per second. So those are the different velocities, and this is what the motion that's going on with this position time graph. The key features on a position time graph. The vertical intercept on an XT graph is always equal to the starting position, which we'll call x initial. That's x sub I. Secondly, the slope of the XT graph is equal to the velocity of the object. And the sign, positive or negative, associated with that slope shows which direction it is traveling. A positive slope means going forward, a negative slope means it's going in reverse. And if the slope changes, then that means our motion changes as well. So now we're going to look at how do we go and create multiple motion representations for an object. Okay, our constant velocity particle model, we treat everything as a particle. and moving at a constant velocity. We can show the same motion with a couple different representations. We have two graph representations, a position time graph or a velocity time graph. We have a mathematical model we can use. We can use a motion map, or we could use a word description. So let's create a velocity time graph. We said before that this has a velocity of 5, 0, and -10. So if I make a velocity time graph, it's going to have a velocity of 5, 0, and 10. Notice that for the first 4 seconds we had a constant velocity of 5, so I draw a straight line at 5. For the next 4 seconds we had a constant velocity at 0, and for the last 4 seconds we had a constant velocity of -10. We can also create what's called a motion map. A motion map is similar to what we did in class when we were trying to create the position time graphs. It's kind of like following the motion and making a mark every certain amount of time. In our class we used a marker on the floor, and every second we put a dot or a little hash mark so we can mark out where it is. So I need a scale, so I'm going to set this up 0 to 40 meters, and it started at a position of 0. The first one, I'm going to circle that dot and I'm going to write the time of 0 seconds. 2 seconds later we are at a position of 30, so I put another dot at 30, and I also label it was 2 seconds later. 2 seconds after that we're at a position of 40, so I put a dot there and I label this one. I've now established a pattern for each dot represents 2 seconds. So 2 seconds later we are still at a position of 40, it hasn't moved, and during the next section it's still at 40. 2 seconds later, at 10 seconds, we are now at a position of 20, and 12 seconds after we've started, we're now at the position of 0. We also go ahead and draw in arrows that represent the velocities. So the first two arrows were a constant 5 meter per second velocity. In the next section, it had a velocity of 0, and in the last section, the velocities were -10. And that's what a motion map looks like. We can also create mathematical relationships. So I'm going to use the equation, the generic equation, x equals velocity times time plus initial position. This is another way of rewriting the velocity formula, except solving it for x. So from 0 to 4, from 4 to 8, and from 8 to 12, we have 3 different equations. In the first section, we have a velocity of 5 and an initial position of 20. So I change my equation to x equals 5 meters per second times time plus 20. And if I plugged in any of those first 4 seconds, it would give me the actual location of where the object is. For the next 4 seconds, we started at 40, and we have a constant velocity of 0. So I get x equals 0 meters per second times time plus 40 meters. And in the last section, we also started at 40, but we have a velocity of -10. So we get that equation. -10 meters per second times time plus 40 meters. Okay, we can also create a word explanation. So my object started at 20 meters, and it moves at 5 meters per second for the first 4 seconds, ending at a location of 40. It then stopped for 4 seconds, and then it switched directions, and it traveled at -10 meters per second for another 4 seconds, finally reaching the origin. Okay, on VT graphs, our vertical intercept on the XT graph is equal to the starting velocity, initial velocity. The slope of our VT graph is equal to the acceleration of the object, and the area on a VT graph is equal to the displacement for that time section. Key features for motion maps. The dots representing the location of an object are at successive time intervals. We always circle the first dot, and the first 3 dots we show the timing pattern. Are we counting by 1, 2, 3 seconds? Or 2, 4, 6 seconds, or 5, 10, 15. So you set up what you're counting by with those first 3 dots. And the distance between the dots is always related to the velocity for that time section. If you have any questions, you can email me at anutzel. This ends our first explanation on how to create multiple representations. We'll be using this when we go into practice 2 and practice 3 next week for constant velocity. Thank you.